Hello everyone. In this video I will go over some examples on equilibrium of a particle in a 3D space and 3D axis. First example. The three cables are used to support the 40-kilogram flower pot. Determine the force developed in each cable for equilibrium. Okay. This is a problem of equilibrium of a particle. Same as before, step one is to draw free body diagram of your particle. So let's see, which point would you pick as your particle? I would pick point A because all DA, AB, AC, and A to the pot are going through this point, so that would be a good point for me. So let's see and let's do in free body diagram. So in 3D way, it's exactly the same. The steps are exactly the same as a 2D free body diagram. Step one is isolate and draw outline of your shape. Step two is to put active forces, the forces that are trying to mess up the equilibrium. Here I can see weight. Again, this is mass, which is not a force, and it is not weight. So pay attention, weight is a force, which is 40 kilogram multiplied by 9.81 meter per square second, and that will give us newtons. Step three is to put reactive forces, forces that are trying to stop this weight, or in other words are providing support and keep the equilibrium. One, I see the cable AC, it is in tension, meaning it's going away. One is AB, parallel to y-axis, AB, still in tension, going away, and there's one going back, and that is force AD. So let me have the axis here, X, Y, Z, drawn for you. That's X. That is my Y, and this is axis Z. All right. So I'll show you different ways of doing these problems, but that was my step one. Step two is to use equations of equilibrium, which in this case we have three equations because sigma fx, sigma fy, and sigma fz are equal to 0. So I have to find components of each of these forces and add all the i's together, add all the j's together, and add all the z's together. So let's see. W, how can I say W in IJK format? Cartesian vector form. So what is the magnitude of W? It is 49.8, so 38 something. And which way is pointing? It's pointing towards negative K. So minus and a K. FAB. FAB, the magnitude is FAB without the arrow. This is magnitude, which is unknown, so that's why I just write it as FAB. And which way it's pointing? It's pointing towards positive J. Okay, let's compare these two these figures, the FBD that I drew and the figure that problem is given. Look where the axis is. It's away, right? The origin is located there. My origin is there. Does it matter? No, it doesn't, because all we care is the direction of the force AB. Here, force AB, which way it's pointing? It's parallel to y-axis, so it's pointing to positive J. Here, it's right on axis that I drew because I decided to draw it right there. Still pointing towards positive J. Doesn't matter. As long as it's parallel to y-axis, it has the same direction as y-axis. So all I have to do is put a J next to it. FAC, you guessed it. FAC, all I have to do is put a plus I next to it. Now for FAD, you have to think back and go back to the examples that I did in chapter 2, where we had a 3D force and I asked you to find the components. So there are two ways to do it. Both will result in the same. Two ways. One is use position vectors. How? AD as a vector equals FAD. How would you transfer a magnitude into a vector? That's right, unit vector of AD. So it will be FAD position vector AD divided by magnitude of AD. So this is one way. The second way, which is exactly the same thing, but we take a shortcut. If you remember from chapter 2, I taught you a shortcut how to do. The X here is 1.5. The Y is 2, but it's minus 2 because we're going back. And Z is 1.5. So remember, the shortcut I taught you, which is exactly doing the position vector but in a much faster way, was FAD equals FAD. Remember, X, Y, Z, they go on the bottom, so 1.5, 1.5, 2. And then X goes up 1.5 I. Y goes up 2J. And Z goes up 4K. This was the shortcut. If you're not sure what I'm doing here, if you're a little bit confused here, go review examples. I think it was last examples of chapter 2 when I do this type of problem. Okay, I explain everything in details in that video, so make sure to go back and check that video. But this is my FAD. I think I have everything now. All of my forces are transferred into Cartesian notation. So let me quickly draw this here for you, because this is going back. So these are the components of it. So if it helps a little bit. Again, you got to go back to chapter 2, an example that I did that looks like this. When you have three forces, remember P, Q, F, it says, hey, write them in Cartesian vector form. That's the example I'm talking about. Okay, so let's see. Now we go back to our equations of equilibrium. Summation of forces in x direction means adding all the i's together. I's together. And make them equal 0. So I have FAC. Let's see. The only I have is right here and right here. So FAC minus FAD 1.5 over square root of 8.5. This has units of meters, this has units of meter. this is equal to 0. Two unknowns. I can't do anything. Summation of forces in y equals 0. All j's add together and equal to 0. So let's see. The j's. This is one and this is another one. So FAB minus FAD 2 over square root of 8.5. Y is minus and then x is minus. So let's go back here. Did I not put minus next to 1.5? Yeah, sorry about that. Because both of these, let's see. Both of these components, this is one component. I is pointing towards minus I. This is the y component of that force FAD and it's pointing towards minus J. This is the z component and it's pointing towards positive K. So both of those are minus and then the K is plus. So let's see if we got it right here. Yes, I have negative equal 0. Two unknowns still. Let's do summation of forces in z equals 0. All K's together. And then equal to 0. I have FAD 1.5 over square root of 8.5. And I have W, which has a K, 49.81. So I keep it this way so you remember where this number is coming from. That's why I write it this way. And this, I have one unknown. I can get FAD to be 76269 newtons, which 3 significant figure is 736. Okay, now I can go back and put them back in these equations. So FAD, when I put it back in the equation, I put the actual number, not 3 significant figure rounded number. So if we put that, we get FAC, the magnitude of FAC to be 392.4 or 392. And if I put it back here, 762.969, I get FAB to be 523.2 newtons or 523 newtons. So we found our three forces. Again, these are magnitude of tension forces in each cable. Okay, let's look at another example, a little bit more complicated. Okay, the lamp has a mass of 15 kilogram. Again, mass, not weight, and not force. I repeat that so you, as soon as you see mass, you know that, hey, this is not a force. Just remember it. It's supported by pole AO and cable AB and AC. If the force in the pole acts along its axis, determine the forces in AO, AB, and AC for equilibrium. Step 1. Free body diagram of our particle. I'm going to pick point A because all of those forces, they go to point A. Remember, in 3D equilibrium of particle, we are looking for a point that creates a concurrent system. Remember? If you remember from last slide of my lecture, concurrent means all the forces go to the same point. They're applied to the same point. And that's the best point to pick as your particle. So I picked part A. Okay, so let me draw my free body diagram here. Have my axis. Step 1, isolate, remove supports, anything like that. So that is my step 1. Step 2, put the active forces. The only active force I see here is the weight of the lamp. Again, not mass, weight of it, which is a force. That weight goes to this point, which we have the dimensions. And I see 3 reactive forces. They're all unknown. And again, as a reminder, unknown force, draw them as tension, meaning going away from the point. So I have basically 3 forces that they go away. One of them points towards the origin, so that's my force AO. I have one that goes to point C, kinda. This is my force AC, and I have one that goes way back to that point B, which is kind of located here. That's my F A B. This is my free body diagram. Remember, these lines that I'm drawing, they're my axis and they're my points. I do not draw the chain, the lamp, the supports, the cables, any of like that. I just put these dots to keep track of where they're going, so they can help me figure things out later and easier. Okay. So next step is to turn everything into vectors. And let's look at the previous problem. The previous problem was easy because AC and AB and W were just on X, Y, and Z, and we had one force that we had to transfer as a Cartesian vector. Here, we only have W, but we have 3 forces. So it's better to start with the position vector and what we've been doing before. So let's see. FAO is going to be magnitude of AO, unit vector of AO. Magnitude AO, which is unknown, that's why I just write FAO. Position vector AO, magnitude AO. Force AB equals FAB, unit vector of AB, FAB, position vector AB divided by magnitude AB. FAC, you guessed it, magnitude AC, unit vector of AC, FAC, position vector AC divided by magnitude of AC. And my W, which is the easiest of all, I have the magnitude of it, 15, 9.8 newtons. So this is magnitude W, unit vector of the direction. So even for W, we are kind of using the position vector, but because it's just Z-axis, we know that it's like this. So it's basically 147.15 K Newton. This one is easy. Again, for W also, we are doing the same thing as FAO, AB, and AC, but because it's straight down, we do a lot of it in our heads. Okay, position vector. We need a lot of position vectors. So let me write or make that table here that we always do. A, B, C, O, X, Y, Z units. Okay, point 8 located at 2, 1.5 minus 6, and the units are meters. Point B is located at minus 4, 1.5, 0 meters. Point C is located at 0, 1.5, and 0 meters. And O is origin, which is 0, 0, 0 with units of meters. Okay. Position vectors and their magnitude. So I go a little bit faster here. You got to go back to previous chapter and previous examples if you have questions or doubts about position vectors. So we have the magnitude of 6.5 meters. Position vector AB minus 6i, 3j, 6k meters. RAB equals 9 meters. RAC minus 2I 3J 6K meters, and magnitude of it is 7 meters. Okay, so I think I'm ready to write the three forces here that I wanted in terms of IJK, or Cartesian notation. 2 over 6.5 I. So basically I'm dividing this by 6.5 I, dividing this by 6.5 J, and dividing this by 6.5 K. FAB magnitude 6 over 9 I, 3 over 9 J, 6 over 9 K, which you can certainly simplify that, put like 2 over 3 instead of 6 over 9. And last one that we need to do is, 2 over 7 I, 3 over 7 J, and 6 over 7 K. The units are newtons. Okay. Step 2 of this whole process was equations of equilibrium, summation of forces, 0, which result in sigma fx equals 0, sigma fy equals 0, and sigma fz equals 0. Let's start with summation of forces in x. All the i's together. So 377 FAO, 6667 FAB, 2857 FAC equals 0. Summation of forces in y direction being 0. 2308 FAO, 3333 FAB, 4286 FAC equals 0. Summation of forces in z direction being 0. 9231 FAO minus 6667 FAB minus 08571 FAC equal 0. 3 unknowns, 3 equations. Again, I'm not going to explain how to solve this. It is expected that at this course you know this, how to solve 2 equations, 2 unknowns, and 3 equations, 3 unknowns. So if you do the final answer in 3 significant figure, I'm gonna see FAO 319, FAB 110, and FAC 85.8 newtons. Okay, let's pay attention to these values that we got. These are the magnitude, and this refers to the sense or direction. Let's go back to our free body diagram. So it was an unknown force for us, so I said draw all of the unknowns going away as tension. So now we got FAO to be minus 319 newtons, meaning it is a force with a magnitude of 319 and pointing opposite of what I drew on FBD. So I should have put it the other way. You don't have to go back, correct your free body diagram. Your free body diagram is 100% correct. There is nothing wrong with it. I'm just explaining what this means when you get a negative magnitude. So pointing opposite, I drew it as tension going away. So pointing opposite, that means it's a compressive force, meaning is pushing on point A, which makes sense, and that's why probably they used a rod and not a cable. If you see AB and AC are cables, so they are in tension, which turns out to be correct. But AO is a rod, and that rod or the metal pole or the wood pole is able to support compression. So we should be good there, and there is no problem there. Okay, let's look at a problem which is simple. So this is already an FBD. This is free body diagram of some problem that we don't know. Maybe a lamp was hanging there, or maybe a weight, or maybe it was for a swing or whatever. But this is now FBD with particle in the center. So all we have to do is, it says find the magnitudes of F1, F2, F3 for equilibrium of the particle. Okay, so this reminds me of a lot of problems that we did in chapter 2, if you recall. So let's see, F1 is along x-axis, so it's just F1I. F2, when they see this line like that, that means it's in ZY plane. So it's just a 2D. So let me draw it here. F2 has an angle of 30 degrees, and this is Z, this is minus Y plus Y. So F2 in terms of I and J has 0I minus F2 cosine 30 J plus F2 sine or cosine 60. I can use that, but let's just be consistent. Sine 30K. Okay, that's my F2. F3, do I have F3? Yes, I do. F3 has magnitude of F3 is pointing straight down, just like a weight that we had. So that's minus K. F4, well, I don't know if we have F4 or not, but we have a 4 kilonewton. So let me draw that also. This one also is in YX plane. So this is X, this is minus X, this is Y, this is minus Y, and we have a force with an angle of 30 degrees, 4 kilonewtons. So I don't know what to call it. Let's go call it F4. Is 4 kilonewton cosine 30, and that is minus Y, and then it is 4 kilonewton sine 30, and it's minus I. That is my force 4. And then I have another one which we can call it 10. It's like this, and that is only in, again, minus X and plus Y plane. It's in XY plane. This one has a slope triangle of 24, 7, 25. It has magnitude of 10 kilonewtons. So let's see, F5 is 10 kilonewtons, and the Y component, doesn't matter if you write X or Y first, as long as you put the I and J in the right place. So it has 10 kilonewton. It's a slope triangle. I'm looking for Y, so I pick this 24. 24 over 25. That is positive J. And then the X component, 10 kilonewton. Slope triangle, I gotta pick 7 over 25, and it's pointing to minus I. And these are all of my forces. Okay. Step 2 was equations of equilibrium. So let's see, summation of forces in x direction being 0. So let's find all of the i's. This is an I, this is another I, this is another I, this is another I. So all of these needs to be added together and equal to 0. So f1 minus 4 sine 30, don't need to include i's anymore, or j or k, 7 over 25 equals 0. Okay, we have one unknown, so I can find f1 from here, 4.8 kilonewtons. Okay. Next one is summation of forces in y. So that means all of the j's I gotta find. I have a j here, I have a j here, I have a j here, 3 j's. Summation of forces in y equals 0. 10, 24 over 25 minus 4 cosine 30 minus f2 cosine 30 equals 0. One unknown again, so f2 is 7.85, 7.09 or 0.1 kilonewtons. And last, summation of forces in z direction. Let's use green this time. So all of the k's, k, k, and that's it. Just 2 k's. So summation of forces in z equals 0. So f2 sine 30 minus f3 equals 0. F2, I just found it to be 7085. And I said put the actual value, not the rounded value. And we get F3 equals 3.543 kilonewton, or 3.54 with 3 significant figure. Okay, this was an easy problem, but it was more for practice. It kind of remind you of what you did in previous chapters. Chapter 2 when coming to solving the problems. Okay, so let's get back to, again, more complicated problems. So very similar to the one that we just did that had a light pole and stuff on it. So again, I see a pole AO, so which I have a feeling that this might be also a compression, but I don't know. I'm just thinking here. Okay, so step 1, free body diagram. So I have y, I have x, I have z. Okay, which point would you pick as your particle? Point A, because you got to make a concurrent system. So let's see. Point A, isolate, remove everything. Force P is 3 kip, 3,000 pounds. And it's kind of going to this point. So, and it's a known force. This is an active force, so 3,000 pounds. What else? I have a cable AC. So now I go back to my reactive forces. So I have force AC. Can I just say AC? Well, no, let's just write force AC. So I don't want anybody to get confused. I have force AB. And last, I have a force AO that kind of goes toward the origin. Because these are unknown, I drew all of them in tension. All in tension. Going away from point A, pulling on point A. Okay. So I have a whole bunch of forces to transfer into position vectors. So I'm going to go through it a little bit faster here. Okay. I have P, which is 3000, position vector AD over magnitude of AD. Then I have force AO, which is magnitude of AO, position vector AO over magnitude of AO. I have force AB, magnitude AB, position vector AB divided by unit vector, or sorry, magnitude of position vector divided by its magnitude. And lastly, I have AC, which is FAC, position vector AC over magnitude of AC. I have a lot of position vectors. So let me make my table here kind of out of the way on the units. So I have A, B, C, D, O. O is located at 0, 0, 0 feet. A is located at 0, 12, 12. B is located at 4, 0, 6. C is located at -4, 0, 6. And D is located at 0, 7, 7. All of them have units of feet. So therefore, again, I'm just going to skip it kind of. Forgot the units there, sorry. 0i minus 5j minus 12k. 5, 12. Okay. This one is going to be FAO 0i 12j 12k 12, 12, which is going to be 12. Last one, oh, it's not last one. AB is 4i 12j 6k. It's going to be 4, 12, 6, which I think is 14. And last one, now last one, AC minus 4i 12j and 6k, 4, 12, 6. This is going to be 14 as well. Okay, so step 1 is just done. Free body diagram of particle A and turning everything into vectors, getting ready for step 2, which is equations of equilibrium. Okay, so now you know the drill from this point on. All the i's together, which we only have 2. All the j's together, which we have all 3. Oh, we have 4 actually. FAO minus 12 over 288. FAB 12 over 14 minus AC 12 over 14 minus 3,000 pounds 5 over 13. So these have units of feet over feet, which they get canceled out, and that's why I didn't include them. So you notice I put the negative here versus I put them here. There is no difference. It's just a matter of personal preference. Where do you want to put them and how it will help you to not get confused. Here, I put this one back. All the k's together, and that should be our equation that we set up for FZ. 6 over 14, 3,000 pounds, 12 over 13. Okay, 3 equations, 3 unknowns. Again, I expect you to do this on your own. And as you can see, we got a negative again for one of them. Doesn't matter which unit you use, because the problem gave us the P as 3 kip. That's why I like to keep the units in kip also, but it doesn't matter what you use. 1.88 kip. Again, AO, I got a negative. Want to remind you again, magnitude, this one is direction of it. Although this whole thing is a scalar, is a direction, but that negative tells us that, hey, this should have been compressive force, but we got it as tension. Okay, so after doing a couple of challenging problems, let's do, now that you know the process, let's do a little bit of an easier one here. Okay, weight W is supported by at A, but bars AB, AD by cable AC. Bars AB and AD are parallel to the Y and X axis, which we see that. If W is 1,000 newtons, determine the forces in each bar. This is weight, which is a force, which is different than a mass, so we can use it on our free body diagram. Step 1, free body diagram. Which particle would you pick? Which point do you see that all forces they point to and go to? Point A. So that's going to be my particle A. Step 1, isolate. Just draw outline. That's my step 1. Step 2, active forces. I have 1,000 newtons pointing down. Step 2, reactive forces. They're all unknown, so I'm going to put those as everything as tension. I have a force AD parallel to x-axis, x minus x. I can move my axis wherever I want and put it anywhere that I see is appropriate. So y minus y, I have a force AB, that's going back, and then of course I have a z force that is going away like this, FAC. Okay, this is my free body diagram. So step 2 is equations of equilibrium. Let's get them quickly ready. Okay, so my W, I'm going to do it a little bit quicker here and less explaining now. FAB pointing minus Y, so it's just FAB minus J. AD is minus FAD I. Doesn't matter, I can put minus next to the I. And then FAC, it is one of those position vectors which you can take a shortcut. You don't have to do position vector, but if you want, you definitely can do a position vector. But I'm just going to do a shortcut of XYZ, and those three go down. So 6, 2, 3 meters minus 2I minus 6J 3K meters. So if you're a little bit confused again, I recommend going back to the examples that I did and explained them. Okay, summation of forces in X, all the I's together, minus FAD FAC minus 2 over 7, because this is 49, equals 0. Summation of forces in Y, AB, FAC, this time I'm looking for J component, so minus 6 over 7 equals 0. Summation of forces in Z equals 0, so minus 1,000 newtons. AC 3 over 7 equals 0. So from here, I get FAC to be 2.33 kilonewtons. I put it back here, 2333 newtons, or 2.3 kilonewtons. I get FAB of minus 2 kilonewtons. Minus. Again, remember, that means this was compression, FAB. I put it back up there, and I get FAD of minus 667 newtons. And that was negative 2. So 2 of my forces basically should have been compressive force in my free body diagram. But my free body diagram is correct. There is no need to go back and correct anything. 100% absolutely correct. But it's good to acknowledge that, hey, these two were compressive and this one was tensile or tension. Okay, let's look at the last problem example that I have here. This is a very interesting one. The 50-pound weight at E causes a 50-pound tension in the cord from C to D. Well, that makes sense because remember, it's just like a pulley system. Remember? We had 5 pounds, or let's say 50, goes around. That one is also 50 pounds. Remember, pulley system. This is exactly like that. It just goes through a loop. It's the same rope. So that makes sense. Express T of CD in Cartesian form. Okay, we can do that. Position vector, done. By using vector dot product, find its components along the slider shaft AB. Note that XD is this much, YD is that much. Color C has a weight W. Oh, instead of 50, find its weight for, or no, color C, okay, for equilibrium. Okay, the first part A and B are just a reminder from previous chapters and vectors operation. So my TCD in Cartesian vector form is the magnitude unit vector of CD. It is magnitude position vector CD divided by magnitude of that position vector. All I need is point C and D coordinates of that. So units are all in inches. C is located at 0, 3, and 4. D is located at 4, 10, and 0. Okay. So if I do the position vector, I will end up with 50 pounds, 4i, this is the position vector, 7j, 4k, over 9 inches, which is going to be 22.2, 38.8, 22.2 k, the units of pound. This is part A. Done. Part B, dot product its component along slider shaft AB. So remember, we got to use dot product of two vectors. Dot product of two vectors will result in a scalar, and that is okay because it asks us about the component, about the magnitude. All I have to do to find the component along AB, component along AB, is dot product of two vectors. That force that I just found, dot unit vector of that direction. Unit vector of direction that we want the component to be on. So, and this will result in a scalar. Vector dot vector equals a scalar. So I got to find unit vector of AB. I have to find components of AB here too. Let me make another table. A, B, X, Y, Z. A is located at 0, 0, and 8 inches. B is located at 0, 6 inches, and 0. Okay. Unit vector of AB, position vector AB divided by its magnitude. Position vector AB is 6j minus 8k. Magnitude of it is 10 inches. So let's put it back here. TCD, I have it. So this is going to be 22.2I, 38.8J. I'm just writing TCD. 22.2K pounds dot this unit vector that I just found, 0.6J minus 0.8K. Doesn't have any units. So remember dot product, how to do it. I's go together, J's go together, K's go together, and do not include IJK because this is a scalar. This is a magnitude. This is a component projection. 22.2 goes to the other side, doesn't have any I, so 0, plus the J component, 38.8, goes to the J component on the other side, 0.6. And the K component, 22.2, goes to the K component from the other side. No IJKs anywhere. I cannot emphasize this enough. No IJKs anywhere. And your final answer is 41.1. So that was part B. Part C now is equilibrium of a particle. If color C has a weight W, find this weight for equilibrium. Okay, step 1 is FBD of my particle. Which particle would you pick? I would pick point C as my particle. Okay, so let's see. Isolate, outline, that is my point C. Active forces. Forces that are trying to move it. I see two. One is the W that they gave us, which we want to find, and one is that TCD. That one is trying to move it. That we just found it. Which, how much is it? It's 50 pounds. It's given. And we have it in vector form as well. Okay, what else? Step 3 is reactive forces. What kind of reaction do you think? What kind of support is this? We had it in lecture. This is smooth contact surface. This C can move up or down very easy. But it cannot move this way or this way. No movement this way, yes movement this way. It's a smooth contact. Smooth contact, recall my lecture, always exerts a force normal to the surface. So this will make a normal force that is perpendicular to this line. So this is my free body diagram. Looks very simple. Looks very simple. So we're going to use a kind of interesting approach to it. Okay? There are two different approaches that we can do. The first one is, look what I'm going to do here. I'm going to take x prime, y prime. In other words, I have a W, I have a TCD, I have a normal force, x prime, y prime. Okay, so if I write summation of forces in x prime should be 0, that means W x prime should be TCD x prime. This component, and this is a 3D force. Don't forget that it's not a flat, it's a 3D space. But anyway, the component along this line, wx prime, should be equal this component tcd x prime. Only if we have the components. So component of w in direction of AB or BA or CA. Let's say in direction of CA should equal the component of TCD on AB or CB. They're the same thing. Okay, I have one of those too already. Look at part B. Part B asks us to find a component of this CD along AB. We already did right here. This is the component 41.1. So I already have it. So let me write this again. Wx prime TCD x prime okay, and of course we have a normal, don't forget that. This one is 41.1 pounds. So component of this W is going to be that. So how do we do that? How do we find component of W along AB or CA? This is C, this is A, this is C, this is B. The exact same way that we found component of TCD on that line. So it's like the problem asks us find component of W along AB or AC or CA, doesn't matter, AB or BA or CA. They're all the same because all we care about is the unit vector of the direction. So all I have to do is find is W dot product unit vector of CA or unit vector of BA. Doesn't matter. I have the unit vector of AB right here. I already did it. Unit vector of AB is 0.6i minus 0.8j. Unit vector of BA is minus 0.6i, 0.8j. Do I have W? Yes, I do. It's just minus WK, because, or in this case is Y actually. Because let's look back here. This is my W, this is my plus Y axis, this is my minus Y axis. Okay. So my WJ dot product minus 0.6i, 0.8j. This will result in minus W 0.8 plus 0 minus 6, and this should be 41.1 pounds, right? So this is going to be 0.6J8K. Let me just make, oh, sorry. Let me just make sure we got it quick. 6J8K, sorry about that. 6J8K, okay. 6J8K, 6J8K, okay. Now it feels better. So this is going to be 0.6 this is going to be, okay, that makes sense. Sorry about that. So minus 0.6 W is going to be 41.1 pounds. Therefore, W is going to be 68.4 pounds. So someone might ask, hey, why did you only wrote summation of forces in X prime? Because I didn't need summation of forces in Y prime. But you can definitely do that. And if you write another equation for summation of forces in Y prime, you should be able to find the normal force. So do a practice. Add a little bit to this problem. Find magnitude of normal force. And let me know if you had questions or there were any problems. Thank you.